Alright, hi everyone. Welcome to this video where you'll learn about the chapter on ionic bonding. So ionic bonding is actually one of the type of chemical bonds in the O-level syllabus, and in time to come you'll learn about the other types of bonding, right? So let's get started. So as you go through this, you'll realize that in your notes there'll be blanks, and if I'm not wrong, the blanks are actually corresponding to the blue font words over here, right? So let's get started first with page 1. At the top of page 1, you'll see that there's this overview about this concept of chemical bonding, and it's split into these 3 points of ionic bonding, covalent bonding, and metallic bonding. So for this part of the video, we'll be focusing on ionic bonding itself, but subsequently you'll learn about covalent bonding and metallic bonding. But just to give some brief information, right? So for covalent bonding is often linked to this idea of sharing of electrons. So using E to represent electrons, and for ionic bonding is usually about the losing or gaining of electrons, right? Which is something that you have encountered in the previous chapter on atomic structure, right? So this chapter is really to build on from the atomic structure part. So just a quick recap on why are we even concerned about these ideas of bonds, right? Why do we want to know about whether atoms should form bonds or they don't form bonds? Okay, if you recall in the earlier chapter on atomic structure, I mentioned about this thing called noble gas electronic configuration, or something that we call a completely filled valence electron shell. So just to recap a bit, you'll learn that in your periodic table, your group 18, which are noble gases, so this all belongs to group 18, they're actually what we call inert as well as stable chemicals, meaning to say that they actually don't go about reacting with other chemicals. And this is because if we look at their electronic structure, they have something that we call a completely filled valence electron shell. So in this part of the screen, you realize that I have shown the electronic structure of all the noble gases in group 18, but just want to highlight that I'm only showing the outermost electron shell only. Okay, so I'm not showing the full set of electrons, because we know that there's always like the first shell, second electron shell, the electron shell, so on and so forth. Right, I'm just showing the outermost electron shell only. And you realize that in general, the first one, which is helium, it will have 2 valence electrons because it's the first shell, and that will be complete. And that is what I call a duplet configuration. For the rest of the noble gases, in your syllabus, okay, note this is just in the O-level syllabus, we say that they all have actually an octet configuration. Octet stands for 8, right? Just like octopus. Octopus means that there's 8 of the tentacles. So this would show that they have all a total of 8 valence electrons. So for example, for xenon, same thing for argon, so on and so forth, right? So basically the idea is that they have a completely filled valence electron shell. Now, then we look at everything else in the periodic table, and you realize that actually all of them do not have a completely filled valence electron shell. Meaning to say that they may have 1 valence electron, they may have 3, they may have 5, they may have 7, but they will never be able to achieve what your noble gases look like. And that is actually the reason why elements actually react. And when they react, they form bonds, right? So this whole concept over here, I just want to emphasize again about how atoms of other elements actually do not have a completely filled valence electron shell is the reason why bonds are formed, right? So if there is a losing and gaining of electrons, that's when we have this concept called ionic bond. And ionic bond, interestingly, when you learn about it over the next few slides and pages, right, you realize that it always happens between metals and non-metals elements, right? So if you recall in your periodic table, you can know where are the metals, where are the non-metals. The other one, which you'll learn in the later chapter, is this idea about sharing of electrons. Now, sharing of electrons is what we call covalent bonding, and covalent bonding only happens between non-metallic elements. So there's a key difference to take note of. But for the benefit of this video, we'll just focus on ionic bonding. Okay, so the covalent bonding is just for info at this point. So let's take a quick look at what exactly do we mean by ionic bonding. In the previous chapter on atomic structure, you have learned that sometimes atoms can lose electrons. And when they lose electrons, they form something that's called a positively charged ion, which we call a cation. So just to quick recap, if you use a periodic table, you can be able to find out the number of protons for sodium, for instance, the proton here is actually 11, and therefore the number of electrons as an atom will be 11. So when you write out the electronic configuration, you realize that it is a 2, 8, 1. And when you think about if it were to form an ion, what should sodium do? And that's why we introduce you the concept that, oh, sodium should lose that one valence electron, which is this one, and then your sodium will actually end up as now becoming Na+, which in terms of electronic configuration is just 2, 8, because it has lost that one. So I hope you still remember about this thing. Similarly, if you go through this whole step of breaking down what should be the ion form, you realize that, let's take potassium as an example. Potassium has 19 protons, which means that in the atom it has 19 protons, and in terms of the configuration, it will be 2, 8, 8, 1. Right, so how can it become stable? You'll lose that 1, and that's when it becomes K+. And that's a configuration of 2, 8, 8. Right, hope you are following so far. And then for calcium, you can work it out yourself. And for magnesium, you can work it out yourself. And you should be able to derive as Ca2+ and Mg2+. Okay, so this was what we already went through in the previous chapter on atomic structure. Just a quick recap. So in terms of how do you draw it out, how does it look like? We say that there's an electron that's being lost, right? So this electron is gone, and therefore you can ignore this entire shell, or this interaction shell will be what we call loss, right? So this entire electron shell will be gone, and you end up with this structure with the bracket and a positive charge, right? So that is how you draw in terms of what exactly is happening. Now, if someone were to ask you why or how does sodium atom forms ion, let's say this is the question, then this yellow highlighted line will be very helpful, right? So how does this yellow highlighted line explain? It first explains by telling us that, hey, look at sodium atom. It has an electronic configuration of 2.8.1 or 2,8,1, right? It tells us what is the original sodium atom. Then it tells us what should happen in order for it to become stable in terms of its electronic configuration or electronic structure. Then you have a 2,8 or 2.8. So this yellow highlighted line is a good way to help us in terms of explaining to people how does sodium atom forms ion. So we try not to use things like, oh, sodium can choose to lose 1 or gain 7, then lose 1 is easier, what should happen? Those kind of things is for us to think through when you're looking at a question. But when you're asked to explain, explaining requires you to show what was it at the start, what did it do, and what did it become, right? So there is a systematic way to explain to people about what exactly happens when an ion is formed. Okay, so those are for my positive ions, and now let's take a quick look, recap on the negative ions, which are what we call anions. So when anions are formed, that's when you gain electron. So similarly, I'm just going to do a quick recap. Over here I have 3 elements, N, nitrogen, sulfur for S, and chlorine, Cl. So over here, we can gain electrons. We look at nitrogen, the number of protons is actually 7, which means that in an electron, in an atom, the electron is 7, which is 2,5. So how can it become stable? Nitrogen will actually gain 3, and end up with N3 minus, because now there is 3 more electrons, 2,8. Similarly, for the other two, go and work it out yourself. You should be able to work out and derive the answer of S2 minus and Cl minus. Don't just take my word for it, don't just copy it down. Try to work through the process and help yourself refresh on the concept. Okay, and you realize that all of them are actually non-metals. Okay, something I didn't mention at the start is that the ones that usually form the cation, they are usually metals, right? So this kind of bring you to the later part when we talk about bonding. Okay, so in terms of the drawing wise, if you recall, because you gain electron, right? So you need to add in an electron in terms of drawing, and we always use a different symbol. So over here I'm using a cross because originally all my electrons are my dots. Okay, and when you draw this out, please make sure you leave a legend. So for example, I'll put a dot. I'll say that this is electron from, I'll just write the symbol as Cl. Cross will be electron from other element, right? Legend is a marking point. Okay, I want to highlight again, legend is a marking point. Without the legend, you will be penalized in terms of your drawing. Alright, and last, this yellow line again. Now what does this yellow line say? It helps us to understand or explain how does chlorine atom forms chloride ion, right? And that's because before that it was 287, then the change was again 1 valence electron, and then it became 288, right? So you see that it's a systematic way to explain to people about what is going on. Yeah, so that will help to address what the yellow highlighted line means. But of course, if the question is asking you to draw, just go and draw something like this. That will be enough to explain to a person. So at this point, it's purely just a recap. I hope things are coming back and it will help you in the next part of the notes. But what I want to talk about in this video is really, now that you've gone through all these things, there's two big questions that we actually didn't really explain to you. First, where did the electron go after the sodium cation is formed? So if you recall in this part, the first drawing here, this electron left, but we never say where did it go. We just show what was the final drawing of the ion, but no one really care about where did the electron go. But it must go somewhere, right? It can't just disappear out of nowhere. Next, in this second drawing, there was a cross that appeared. So where did that cross came from? It must have came from something. It cannot just be plucked out from the space and just added to the chlorine. It must have came from something. And now if you piece these two questions together, you will realize that actually what likely has happened was that this electron from the sodium was the one that came over to the chlorine, and the chlorine actually gained the electron. You form both of two sets of ions, and that's where we call an ionic compound is formed. And that brings us to what this video is about, focusing on ionic bonding, right? If you're feeling a bit too tired, the video is taking too long, feel free to pause the video because there's still a long stretch to go. Then after that, just come back and refresh your mind so that you can start, right? So I'm just gonna move on to page 3 now to introduce you to this concept of ionic bonding. Alright, when it comes to the formation of ionic compounds, now this is when things get a bit interesting. So if you are curious to look at what exactly happens when a reaction takes place, you can scan this QR code, you can click on this link to go and take a look at the reaction between sodium metal and chlorine, right? And how does they actually come together to form this thing of sodium chloride. But in this video, what I want to talk about is really in terms of the electrons, in terms of the drawing, how and what actually happens when ionic compounds are formed. So in the formation of an ionic compound, what happens was that each of the sodium atom actually loses one electron to a chlorine atom. Now, let's link back to what we learned in the previous page. Sodium atom was 2,8,1, right? When it goes through the reaction, it actually becomes 2,8, and therefore there's one electron that's lost. So that's what this statement is trying to say. Chlorine atom is 2,8,7. When it goes through a reaction, it now becomes 2,8,8, right? So this is what this question is trying to say, this statement is trying to say when we say that there's actually one electron that went over, and therefore it becomes ion for both of them. Now what happens is that both of the atoms are what we call stable electronic configuration, and therefore they're now both ions. Now when you have a positive ion and a negative ion next to each other, it's just like how a north pole and a south pole will behave. They will start to attract each other. And this attraction is an interesting concept because it's what we call an electrostatic force of attraction. It is between electrons, it's between positive and negative charge. That's why it's called electrostatic. And it must happen between oppositely charged ions. That means it must be between the Na plus and the Cl minus. It should not be between Na plus and Na plus, right? That is like a north pole and a north pole. It should repel. Okay, so how this concept works is that what you end up with is this structure that you see over here, looking very, very complicated with a lot of spherical structure here. But what it's trying to show you is that you end up having a sodium, which is a grey color sphere, surrounded by the chlorine, which is a green color sphere, and the chlorine, because it's a Cl minus, it will be surrounded by then another sodium, which is a plus. Then the sodium will be surrounded by a negative Cl minus, and this repeats over and over and over again. And that is what we call a lattice, or rather ionic lattice structure. So a lattice is a bit like many HDB flats being stacked together side by side. So you can see over here in this other drawing here, it's as if there is a lot of units of flats being lined up next to each other, and that is what we call a lattice structure. Okay, and this whole lattice structure is being held together by, once again, very strong electrostatic force of attraction. And this electrostatic force of attraction is actually what we call ionic bond in terms of laymanterm. Okay, unfortunately, we don't accept if the student use ionic bond to replace this electrostatic force of attraction. You have to use electrostatic force of attraction, okay, to explain what this attraction is. Alright, so that is how the lattice structure looks like. But the good news for you is that you don't have to draw this thing, right? If you want to draw this thing out, I think it'll take super long. So instead of showing this kind of structure, what we do is we teach students to draw something called a dot and cross diagram. So how does the dot and cross diagram looks like? It looks like this one on the bottom side, and in particular the right hand side. So the right hand side of the drawing is what we call the dot and cross diagram. You will have to practice this out later on using worksheet 1 and worksheet 2, but let me just explain a bit about what's going on here. This is essentially what we spoke about in the previous 2 pages, how sodium actually can become an ion, how chlorine can actually become an ion. The only difference is that now you have a complete picture instead of looking at sodium by itself and looking at chlorine by itself. But now you look at them together as one set, and that explains why the cross came about over here. And that shows you that actually what happened in this reaction was sodium passed one electron to chlorine, and in the result both of them become ions. And that's why the legend is important, right? Without a legend, imagine you draw everything in crosses. No one is going to understand you in terms of where the cross came from. If you draw everything in dots, same thing. If you draw cross and dots, but you don't write a legend, same thing, nobody will understand where or what the cross is supposed to mean. So a legend is crucial, like what I mentioned earlier. And that's why we end up with this term called dots and cross diagram, right? That's why we say that you should draw a dot and a cross to represent the electrons, right? And this is what we need to focus on for worksheet 2, I believe, in terms of the drawing. Okay, so with that, I'm gonna move to the next pages, which are the slides, to kind of show you, bring you through what I call the properties of ionic compounds. So in this page, in this part of the video, I did go through how ionic compounds form. I'll repeat a bit more in the slides, but after that, we'll go straight into the properties. That means melting point, boiling point, solubility, can they conduct electricity, so on and so forth. Alright, for this part of the video, we'll be focusing on having more visual representation of how ionic bonding looks like, how the ionic compounds form. Okay, so in the previous few slides, not the previous lesson, the previous part of the video, I mentioned to you about how metals can actually form what we call cations, positive ions, and how non-metals can form what we call negative ions, anions. So just a bit of a recap, they form this because they will gain electron, and on the other side is because they lose electron, right? And what actually happens, right, in terms of how do they come about, is because when there's a metal and there's a non-metal, one willing to lose, one willing to gain, and they react together. So this is actually the result of a reaction. So this arrow here and this arrow here is actually representing an election, and the reaction will help us to address how they actually come together to then form what we call ionic compounds, right? And I mentioned just now that ionic compounds that exist in what kind of structure is what we call giant ionic. Not just giant ionic structure, but to be more exact, giant ionic, just help me add in a word over here, lattice structure, right? I mentioned just now that it should be a lattice structure. Okay, so this is what this whole part of the chapter is about. So they come together, forming a reaction. The compound is called ionic compound. It has a giant lattice structure. So Just going to quickly run through again about the structures, about how the properties are like. This is what I mentioned earlier. We know that in ionic compounds, there's this thing called strong electrostatic forces of attraction, right, over here. And we want to understand how does that affect the physical properties of the chemical. So very quickly, I mentioned in the previous slide, right, that actually what happens is when the sodium and the chlorine comes together, they react, and in the process they form this kind of structure. Now this is just one set, but if you think about it, inside sodium and Na, there's actually a lot of the sodium atom which can form a lot of the sodium ion. So what will happen is that there'll be many sets of this thing and many sets of this thing, and they will all come together, and that's where we end up with a structure, right, which is our lattice structure. And if you look closely at how we draw this thing, do you realize that we have a positive here, then it's followed by a negative, then next to this negative, we didn't draw another negative, we actually draw a positive, then we draw a negative, then it's alternating. What is actually happening here is because they are oppositely charged ions. You can never put two positive together because they'll repel. You can never put two negative together because they'll repel. So take note that you always draw it in an oppositely charged manner. So this is what I've mentioned just now, and with that, that's where we form this whole structure called a giant ionic lattice structure. So same thing, help me to add in this missing word of a lattice, right? And the lattice structure will show you how the sodium and the chloride ions are actually arranged, and you realize that they are also alternating each other. That means one chloride will be followed by one sodium, so on and so forth. Okay. This is also another diagram of how a giant ionic lattice structure looks like. We're just showing you this through what we call a ball and stick model. So a ball and stick model is something that you can actually buy online, right, from Shopee, Lazada, and you can go and fix it yourself and see for yourself. It works a bit like a Lego, but each of the lines is trying to show you how are they attracted together, and this helps us to see that there's a green one, followed by a grey one, followed by a green one. The idea of oppositely charged ion. You'll see this again and again and again, right? So I think this would be a good diagram to show you what exactly is this idea of lattice structure. So what is interesting about this structure? What are the properties that comes with it? If you flip through a textbook, if you look at the notes, you realize that we have actually labeled the textbook pages. Please go and read through it so you know what's going on, and it is really very important for you to familiarize yourself, because properties of all these compounds, right, is a frequently asked concept. Okay, so first, what we've learned is that all these ionic compounds, they have very strong electrostatic force of attraction. And not just being strong, you realize that it must be between oppositely charged ions. See, so you keep saying this word over and over again because you're trying to explain to people that it's between plus and minus, not between plus and plus, right? So this is a key concept that must come out. Now, when you have strong attraction, if you think about you want to melt something, you need to put in energy, right? In the earlier chapter, we learned about absorbing energy to overcome force of attraction. Now, if the attraction is strong, the amount of energy that you need must definitely be large amount of energy, right? Only when it's large amount, then you can work against this strong electrostatic force of attraction, or we use this word overcome, right? So some of you mentioned to me before, can I use the word like break, right? I mentioned that no, this is not acceptable, because you're not really breaking anything, you're trying to overcome this attraction. So take note of the phrasing of the concept. And when this thing happens, we need a lot of energy, that's why you end up with high melting point and boiling point, right? I hope this is clear so far. Next, in terms of solubility, right? What about these ionic compounds? Interestingly, they are usually soluble in water, but what we call insoluble in organic solvent. What does that mean? It means that it will dissolve in water, but most of the time it should not be able to dissolve in organic solvent. So question that I always get is, what exactly is organic solvent? At this point in time, the most obvious one in your syllabus is just oil, but as you go through further until Sec 4, you will learn that there will be other things such as what I call hexane, so on and so forth, right? But for now, don't worry so much about it. Just know that soluble in water, but insoluble in what we call organic solvents. Why is that the case? Now, that's the case because water molecules, interestingly, it is more of like a beyond secondary school concept. Water molecules can actually separate the positive ions, meaning to say that, remember just now we have this all the structure that looks like this, right? What we are saying is that if you have water molecules, they can actually split all these gray lines that you see over here. And when it does that, that's when your compound would have dissolved, right? So what happens is that water can do that kind of thing. In terms of the exact reason why, we can talk about it in class, right? But not in this part of the video. And rest at this water, I've shown all these symbols, weird looking symbols, right? What do they actually mean? Just for your info, this symbol here means delta, right? Delta means small amount. Okay, I will also go through a bit more about this in class itself, right? So in case you are curious about what is this weird looking symbol with a plus or negative sign, this is what we call delta. Okay, and of course, I think we just want to highlight again that for water molecules, in case you're not too sure, they are what we call covalent compound, not ionic. But for now, you haven't learned about covalent, so you won't really appreciate how the water is like. Okay, so as mentioned in the previous slide, there will be all these delta, negative sign, positive signs, which I'll talk a bit more about in class, so don't worry too much about this. For now, just need to make sure you remember whether it is soluble or insoluble. Okay. And for the very, very last part of the properties, so there's a lot of 3 properties you need to think of. Okay. This is the last one, which is about whether can it conduct electricity. Interestingly, ionic compounds can conduct electricity in the aqueous. Aqueous will mean that when it's dissolved in water or in what we call molten state. Molten is basically liquid, right? That means it has already melted. So I just want you to make sure that you know what's the difference between liquid melting and dissolved in water. So I'll give you an example. Okay, melted salt is called molten because it was already melted, right? But if I have something like salt solution, then we don't say that it's a liquid, we say that it's actually an aqueous chemical, right? So I think that's something you want to be very clear about now. I know in lower sec or in primary school, we tend to think of liquid and solution as the same thing, but they're actually very, very different things. Okay, so for ionic compounds, interestingly, they can conduct electricity in aqueous or molten states, but not in the solid state. Why so? It's because in the solid state, they do not have what we call free mobile ions. Now, what does mobile means? Mobile means free moving. That means in the solid state, the ions actually cannot move. And when they cannot move, they cannot act as what we call charge carrier to conduct electricity. In the aqueous and molten state, you have this thing called mobile ions, and then they can act as charge carriers, and then they can conduct electricity. Okay, so to understand this, I'm just going to draw a symbol diagram, then we take a look and see if it makes sense to you. So let's try to imagine this is what is actually happening. Imagine you have a beaker of water. Okay, when you add in this ionic compound, imagine it looks like this. What actually happens when it's inside the solution is that the ions start to separate. So you have some positive ions here, you have some negative ions here, you have some negative ions here, you have some positive ions here. And what is interesting is that all of them can actually move because they are in aqueous in the solution. They can actually move around, they can actually travel around the whole solution. And that is what we call charge carriers. Okay, charge carriers are present. Compared to if you just have a solid state ionic compound, inside this solid state, what will happen is that you still have your negative charge, you still have your positive charge, but they're arranged very neatly in this lattice structure, if you recall, right? Alternating one another in terms of the charges. You end up drawing things like this, this. And what happened here is that there are no free mobile ions. Why is that the case? Because they are held in fixed position, just like in a solid state. So they cannot move, they can only vibrate and they cannot move around. If they cannot move around, right, so this doesn't happen, then they cannot carry the charge. So this is something to think about when we talk about the whole concept of, are there charge carriers or are there no charge carriers? Okay, so you can pause the video now to take note of this drawing to see what it looks like. We can run through a bit more of this concept back in class. So in summary, what have we talked about so far? There's 3 key properties that you must know about ionic compounds, very important. 1 is really about the high melting point and boiling point. 2 is that they are usually soluble in water, but insoluble in organic solvent. And last is that they can conduct electricity in aqueous or molten state, but not in a solid state. Right, so with that, we have come to the end of this video in terms of the objective. In terms of the work that I need to do now is basically worksheet 1 and worksheet 2. Okay, so if you are having any difficulties with worksheet 1 and worksheet 2, you can watch the next 2 videos, which will provide a bit of a guide on how to attend the questions there, and then we'll go through all these things when we come back to class. Right, that's all for this video. Goodbye.